Well, so talking about a project I've been working on for a while now. The title is Voraldo, and it is a GPU-based volume editor. And just for some background, kind of to explain what that means, most familiar reference for most people is Minecraft. That's maybe the first place you hear the word voxel. The typical approach to rendering these is to, it's called indirect volume rendering. So rather than so basically it's creating an intermediate representation that is used to represent the voxels. So here there's different ways to establish thresholds for inside and outside and create a mesh there. There's marching cubes, dual contouring, and just creating meshes on the faces of voxels that have empty neighbors for Minecraft. So my project here is doing what's called direct volume rendering. So rather than using an intermediate representation, I am using that image data as if it were sort of a solid thing. There's a high resolution buffer of RGBA values, and there's different ways to manipulate it. Along with that, there's a 3-channel lighting buffer, which is used to scale those values, and there's different ways to put values in, which I'll explain a little bit later. So loading and saving is done with basically the same format that you send it to the GPU in. It's enumerated slices. If you were to imagine this vertical face here is one slice, I'm creating a very tall PNG that is slices one after the other, kind of vertically listed out. So that's a few megabytes versus something explicit for every voxel would be hundreds of megabytes, and that's what it is in GPU memory. So altogether with 512 resolution blocks, you're looking at like a couple gigs of GPU usage. It does get pretty heavy. So yeah. Does somebody have a question? Oops, sorry. Okay, anyway, yeah, so color is front and back buffer that have RGBA values, and those are 8-bit unsigned integers. Masking is a single channel, 8 bits, and lighting, same, but I'm going to be converting that to floating point. And there's a couple other changes that are going to come along with that, but currently it's an 8-bit unsigned integer, and we'll see later where that can kind of clip, and there's some issues there. But so this idea of masking comes from raster image editors. So there's more flexibility in like Photoshop, but in this particular case, it's just used to signify that this portion of the 3-dimensional raster is going to retain its value to some degree. So if something then draws over it, here, just to illustrate that, I have the default initialized XOR texture. And then I've masked off several sections of it. On the right, it's very high value, decreasing to the left. So basically what that looks like is, then I went over with just a sphere that's large enough to cover the entire volume. And based on the mask value, the output, or the final voxel color value is is determined based on a blending operation that weights the drawing operation with the existing value there. So the ways that those are set, there's two sort of universal, like sort of Boolean type things here. Unmask all, or set all to some level, and then invert mask, which inverts it. So in value of 0 becomes 255, 255 becomes 0, this type of thing. Mask by color looks at the values in each of the channels and can be used to mask certain ranges. This is interesting when you have like diffused color with a blur and you sort of establish sort of a threshold there based on this. So it's something interesting you can do, and I'll get into that a little bit more later. But so any of the drawing primitives have the option to also mask any of the affected voxels. So there's two main classes of drawing operations, and there's the sign distance field primitive based ones, which use an isInside function, which does a couple other things, which I'll explain. Well, we'll get there. But and then the other uses a separate piece of excuse me, GPU memory as a load buffer, which copies raster data from the CPU, and copying from that is done in a way that respects the mask. So it's not just directly loading data from the CPU into your front buffer. It's selectively applying it based on the mask. So that's used for loading PNG models that you've saved, or it's a very cool algorithm. I talked to the guy, Brent Wernes. He's very cool. Look up voxel automata terrain. I'll show you some pictures a little bit later, but it's a very cool noise generation algorithm. So the most basic shapes, we've got a function that basically says, for my voxel location, am I inside or outside of this shape? So axis line bounding boxes, or this sort of a cuboid shape that's orientable. Cylinders and tubes, spheres and ellipsoids. So that's a sphere with a couple different radii that you can set independent of one another. And you can rotate that too. Rotated grids, which I don't have any pictures here, but I'll I'll get to one in a second. Height maps are very cool. You can see one in the top there. Basically, comparing, it's a scalable height, and it compares the like the Y value of the voxel location against another texture to determine that one. So noise on the bottom there, I'm using Fast Noise 2, which generates a lot of different algorithms, noise algorithms. And basically the way that that's used is there's a user specified upper and lower threshold that says, all right, this buffer holds noise values that range between 0 and 1. I want to affect the ones that are between like 0.7 and 0.9, and that would mark that would do that, right? So it would any noise value that's red that's between 0.7 and 0.9 is going to be drawn to. So triangles, they're based on 3 points, and then basically those 3 points are in a plane, and I create sort of like a prism type shape that's a little bit above and below that plane. So you can see two of them put together. Isosahedron is actually composed primitives. It's tubes or cylinders actually, spheres at the points and triangles for the faces. And then there's user scripting, which is not quite done yet, but basically you can do some very cool stuff. You can create fractals. You can do some very, I don't actually have very good pictures of that right now, but yeah. A lot of the things on here have been hit with a pretty heavy Gaussian blur, so that's why they look really smooth. So here's just kind of showing what these composed primitives do. In the previous picture, you might have seen that isosahedron sitting on that piece of landscape. This is just a chunk cut out of the middle. And so basically, with the lighting already computed before the slice was taken out, you can kind of see the dark patches where light didn't penetrate as deeply into the object. You can see thinner parts on the faces where light did shine through. So that's kind of a cool little effect there. And so the sort of hazy volume around the shape as well is created by putting the alpha value sort of in the lower ranges versus putting it at 0 for the slice there. So the load buffer type of drawing operation, these are some voxel automata terrain outputs. So basically, I generate all that voxel data on the CPU, put it in a texture, invoke a shader that has some logic to do that copying operation. So, right, and that copying operation can either respect the mask or just overwrite everything, depending on the behavior you want. So, a couple utility operations, blurs of adjustable radius. So basically, combining my value with my neighbor's with different weighting. Clearing, similarly to the copying, respects the mask value when invokes. Masking operations I talked about earlier. The shifting is basically, if I were to want to translate something into X, Y, or Z, and have it loop off the edges. So if it's like a, I've heard it described as a torus, but that doesn't really geometrically make sense. Just the way that it kind of loops off the edges in all 3 dimensions. It's, yeah, a little abstract, but basically it just loops off the edges when something was would translate out of the volume. So the operation logging, this is actually very cool. This is something I've been working on the past 3 or 4 days pretty seriously. It's not exactly done yet, but it's basically, the idea is like everything you do in the editor is logged to a list of JSON records of like types of operations and all the parameters to that operation. And I can dump that to a text file if I want to replicate something that I've done in the editor. Basically, this JSON scripting is like, I can load some formatted input file that says, I want to make an animation. Here's the setup, and then there's per frame operations I can specify as well. So it's kind of, it facilitates the making of these frame perfect looping animations, which is cool. And with GL read pixels, I can get the frame buffer data with the, there's a little bit of finagling to get rid of all the aliasing later. I'll go over that. But basically, once that's all done, I can get that image data directly with GL read pixels. So this just showing basically you can create a lot of complexity with oriented grids. So this has some animation of the lights over time. It's maybe a little too subtle to see, but you know, it's something to work on. Point lights you can animate as well. I don't have any examples of that yet either. But so basically the way this is achieved was with the default XOR texture in place, I went and masked a sphere at the center. Then drew everything with a clear, and then I unmasked everything. Okay, then I went through and for the first one of these spheres that's colored, I masked with a value of 255, and then I inverted the mask. So that is basically what that means is inside that sphere is 0, and then everything outside is 255. So then my drawing operations are constrained to the volume of that sphere, right? So sort of a constructive solid geometry kind of idea. But anyway, do that same thing 3 times. And because of the way that the whole buffer except for that sphere is masked, the drawing operations are constrained only to that sphere. So kind of cool. And then, like I was saying, the per frame operations here is a little bit of rotation, and then in this one, some changing lights. So the lighting operations, there's basically a level clear, which basically sets the whole buffer to some RGB value. And that's, like I say, it's a scale factor for the color data. And that's how sun shafts, that type of thing, are represented. It looks very flat when you have no lighting on it, right? Because anything that shares a color value, there's going to be no depth cues, unless there's something with some alpha to give you that depth cue. But anyway, so these types of lighting create that illusion. Things like point lights, cone lights, directional lights, fake global illumination, and neighborhood-based ambient occlusion. And I'll go over each of these. So the direct lighting is basically, it's modeling a ray traversing the voxel space and being attenuated as it travels, where attenuation is just the signal is decreased in magnitude, right? So it's becoming dimmer as it hits opaque objects. So the amount that it's affected is so the alpha channel value is raised to a power, and this is to give you more usable range. Same way that I do later in the alpha blending for the for the color data. So the for the direct lighting, shader invocation is per voxel, and basically for a point, it's got a point in space that represents the light location, and it's going to sample the alpha values in between the light location and the voxel that this shader invocation represents, and then consider the distance. Once all the attenuation is computed, there's another attenuation that happens to model the inverse square law, which is like a 1 over distance squared. Anyway, the directional lights specify like a uniform direction that the light originates from for every voxel. And that's done with 2 angles. Here, just the azimuth and the altitude. I call them theta and omega, I think, I don't remember. But just 2 angles. And that's sort of general enough. So fake global illumination. It's not very good fake global illumination, but it's kind of a real-time approximation. It's invoked in slices down the y-axis, top to bottom, right? And there is synchronization in between each slice, so it is not exactly the fastest thing in the world. So basically, each cell in each slice, horizontal slice, considers 9 rays going upwards, and that's to, you know, if you kind of look at it from above, it's the whole neighborhood above it. So it's going from that voxel's location to those 9 voxel locations, and so each of those rays has some contribution to the final lighting. If it hits something that's opaque, it takes some of the light from that opaque object, and if it escapes the volume before it hits anything opaque, it's going to use a sky color as its contribution to the lighting. And so all those are averaged, and then that's what's applied. So neighborhood-based ambient occlusion is very similar to the Gaussian blur, the way that the alpha values are weighted. It's kind of like a almost like the inverse square law thing too. It's like 1 over the distance squared kind of a thing. If you consider the middle one as like an origin point. So we're determining an alpha fraction that is the sum of all the sampled alpha values over the maximum possible alpha values that you could see if all samples were, at some maximum value. Here, 255. And so the light in the buffer is then decreased by multiplying it by 1 minus this fraction. So got one here with some lighting data applied to it. You can see a little bit of aliasing, which is kind of the next big thing I'm working on, is multi-sampling in the voxels for the shapes. So like you can kind of see on the faces of some of these grids where there's rough spots where it's just aliasing. You can see some lines there. Anyway, but this is a good demonstration of the attenuation of light through sort of a transparent, just a low alpha volume, and kind of the appearance of that, and the way that the light also diffuses into things that have kind of a medium alpha. If it's strong enough, it sort of penetrates the sort of the grid there. And so it like I was saying, the rotated grids very quickly create some very complex kinds of structures, which I think is very cool. And so this one is zoomed way in to kind of give you a better view of this aliasing, and kind of give you a sense of the scale of the voxels. This is done with nearest sampling, where typically I do mapped nearest sampling. So you can see individual voxel borders a little better here. But so this is another, this is the same volume. So you can kind of see the same sorts of features. And on the surfaces of the grids, you can see that same sort of issue that multi-sampling might be useful for. So the rendering, basically, you can think of it logically as if it were taking place in the fragment shader. And so basically, that's per pixel, right? Each pixel considers an array computed from glfrag chord, goes out into space, tests against an axis-aligned bounding box that contains all the voxel data. If it hits, I know where the near and far intersection points are, and I can continue. If it misses, I know that there's nothing to be done. I didn't hit the volume, and I just used the OpenGL clear color. The indications that hit, they're going to look through that volume. And I found this very appropriate picture on Wikipedia. Just was looking for a picture that was samples along a ray. Somebody had made this. It's on Wikipedia, but it's not on any page, which is interesting. But anyway, so basically alpha blending is done by taking these samples and back to front, compositing them over one another to create the final output color. And there's probably room for optimization there if you go front to back, but the alpha blending equation that I found was for over compositing. So like I say, there's probably some way to make that a little better. If you were to composite forward, you could stop at some threshold maybe. So anyway, some of the optimizations that have kind of developed over the past few versions of this. There's a render texture that really enables a lot of things. So the dimensions are basically kind of set at compile time, but you have this super sampling factor that says, all right, I have this render texture. How many times higher is the resolution of that texture going to be than my screen's resolution? So less than 1 means there's less than 1 pixel behind each output pixel, correspondingly greater than 1. You have super sampling, right? But this makes it flexible enough that I can use it on my laptop with an Intel integrated graphics chip, or on my desktop with a pretty serious Radeon card. So this is like, kind of a cool application for this. But so the flexibility to use those different resolutions when you wouldn't necessarily be able to. Okay, so imagine you went to a really big texture. Well, then maybe you're when you call the function to dispatch the compute shader, there's some maximum value for each dimension. Basically, the way I got around that is I made a tile-based renderer that just goes in squares, 256 on a side, and fills up that texture, basically. There's no synchronization in between each of them, so it's very fast, because they're all independent. So basically, another thing from the render texture is that you don't necessarily need to update it every frame, right? So it's potentially the same data, right? So it's just kind of busy work to be recomputing all that alpha blending, all that stuff again. So basically what I'm doing is reading the final result back from the render texture unless something changes. And so to take advantage of the super sampling, and this actually, it's kind of cool. This is enabled a lot, sorry, this has got rid of a lot of aliasing and created a really very smooth image, I think, at this point. So basically, when this sampling is done, right, to put the pixels on the screen, I have a triangle that covers the entire screen, but then I'm sampling the render texture with linear filtering, and I'm using a multi-sample buffer when sampling. So I have offset samples that I'm blending to get the final output color. And kind of playing with like the idea of doing some dithering at that stage, because that's where I do my tone mapping, and that all kind of rolls into that floating point lighting texture thing. And it's a little bit complicated. If anybody's interested, I could talk your ear off about it later. But the basic idea is that you've got a lot of data that generates the output pixel. It's a lot of it's all averaged together to get that final color. So pretty basic libraries. SDL2 for windowing input handling. I only need 4.1 for compute shaders and image load store. GL3W is a replacement for glue. And I have the source for it, which has actually proved helpful at least twice. Yeah, so DRM GUI, I moved to the docking branch just recently. There's some very cool features with that. GLM for vectors. Fast Noise 2 I mentioned before. They've got a very cool, very configurable noise generation library there if you want to check it out. And then there's load PNG for PNG, like input and output. Then just the JSON library, and this is kind of an example of like what those formatted function calls look like. So if I wanted a Gaussian blur of some radius n, that's kind of what that looks like. And again, I encourage you to look at Brent Wernis's voxel automated terrain. It's a very cool thing. Basically, his implementation was in processing, and I converted it to C++ and made sort of a header out of it. So I had actually quite a bit of finagling with this because Java has a built-in like unlimited number of bits kind of number system. It's like they call it big int. Anyway, it's arbitrarily large integers, and it's used to encode rules for this noise algorithm. Anyway, so there's a little bit to that if you do actually want to use it. So yeah, that's everything. If anybody has any questions, I'd be happy to answer them.
Have you thought about using some sort of background image or cube map, 3D map, whatever, so that instead of sampling the clear color whenever the ray gets through the volume, you instead sample from that image?
It's actually a very cool idea. Yeah, that might be worth looking into. I hadn't considered that. Something I had thought about recently was the initial ray generation, doing some sort of either perspective projection or trying to do like a I don't know, it's like a lens curvature to it.
That was leading into my next idea or thought was, can we like put a snow globe model around it so we get this? It frames the volume so it isn't just petering out into space, but like as a inside of a glass sphere. And then you're talking about doing lenses, and then you could throw that in there.
Yeah, a lot of potential. So there was something on the graphics programming Discord recently that was, I think it was today actually, the Embergen. I don't know if you've seen that. I mean, they're doing like volumetric simulation type stuff with rendering that's like this kind of stuff. It's really very impressive. But animated volumes like that.
Yeah, I saw that, and it looks really cool. But it definitely seems to be, I don't know. It's not voxel based. Yeah, that's the link here. Do we want to?
Yeah, sure. Yeah.
No, well, I was like, let's finish what we're talking about here, so we can end the recording instead of getting distracted.
Gotcha, yeah. Sure. I can do a demo if you guys want to see something.
Sure.
Also,
I was also curious, like, is there anything causing the like kind of like fog you have going most of them, or do you just kind of have a bunch of like transparent values?
So yeah, that sort of volume fog there. That's so that's kind of ranges of alpha values, kind of in between like 3 and 7. So it's just that's a kind of very transparent end of the alpha scale there.
Okay, that's cool. It's a really cool effect.
Yeah, I dig it. Yeah. Sorry, I just had to fix one thing.
So have you guys thought of like using some acceleration data structures for the triangles itself, and then trying to run the rays from that?
So there's one triangle.
Pardon?
There's only ever one triangle. So there's no meshing.
No, there's no meshing at all. Okay.
So yeah, it's it's called direct volume rendering. So you're compositing samples of RGBA data inside of that volume.
So it's all in a tube.
Right. Yeah. It's all inside that three-dimensional texture.
Okay. Great.
Okay.
So cool to do stuff like depth of field and stuff like that.
That would be
look
cool
really
too.
nice.
Well, I do have mipmap set up, so it might be something I could do to blend with a higher mipmap level to do that blurring. I don't know much about mipmaps. I have mipmap samplers, but that's just about it.
Do you have any like kind of like end goals for this project, or?
It's been constantly evolving. It's kind of been part of my growth as computer graphics programming. I don't know. It's really it's turned into quite something, I think. Let me see if I can change which screen this points to. Awesome. Cool. So this is the default initialization. It's an XOR texture. This is kind of a classic computer graphics thing. That's like each of the, if you were to look at like texel coordinates, they're in the range of 0 to 256, or in this case 512. So basically it's that number considered as a binary number XORed with, so it's X, Y, and Z is XORed, and that sets the level for that pixel's content. So it's, I don't know, just kind of a classic test pattern. But it's just something to show that it's working, I guess. Because that's been an issue. I've been trying to get it to build on Windows and only had limited success there. Basically, one of the primary things there is it'll show up, but I think the latest I've sort of figured out is that it sets up incomplete textures, so there's no allocation of a buffer behind that texture. So that may be some indication of how to fix it. I think that it had been done with like null initialization, but then I think if I give it data, it allocates something, hopefully. So that's something I have to get a hold of somebody with a Windows computer and try again. But yeah, so basically, say I want to do some mask this and so basically that's cut out a height map. So you draw on a height map, and then and that first height map is masked, and then drew another one that has 0 alpha, and that didn't mark over these voxels that were masked. So basically, if I clear the light and then do a point light sort of in the middle, you'll be able to kind of see what goes on with that. And interface maybe not ideal, but yeah, you can kind of see the way that shines out from that center point there, and shines through alpha values to varying degrees. Direct lighting, again, that's the two angles. So you can kind of yeah, and then
Yeah, that's pretty cool.
if anybody wants to see anything in particular, I could honestly just mess around with this for some period of time.
Are the height maps always drawn from the bottom up, or can you do like 3D noise or something like that?
So, good question. Yeah, so I have a couple different generation algorithms, but they are all just drawn up the y-axis right now. Yeah, so yeah, you did pick up on that. The voxel automated terrain, I have it set up so that you specify which faces to fill. So yeah, there's no reason why it couldn't be like you're suggesting. You know, from whatever direction. So let me kind of give you some indication what that looks like. So, and this actually will take a second because it's generating, what is it, like 100 million samples or something, or 100 million voxels. Right, and oh, that actually was still masked. So mask all, and then do that again. But basically, this is just kind of a way to get some really exotic patterns in there that you can do cool stuff with the rest of everything here. Let's see what we got here. There we go. So there's something interesting. And it's kind of maybe what that looks like. So, does anybody have any questions about anything, or
Just admiring the really cool pictures.
That's pretty cool, yeah.
I have I'm writing up a thing for my website about this, which I'll put in the graphics programming meetup Discord if you guys want to see it.
Oh yes,
I
absolutely.
I have a research paper kind of thing that I wrote about it too. It's kind of in the style of an academic paper, but it's not finished, and a lot of details need to be kind of rehashed. But yeah, that might be. I'll link that now, actually.
So for each of the voxels, the coordinates are actually varying from 0 to n or whatever in X, Y, and Z, correct? So
Yeah.
So
In terms of
there's something called a Morton code.
Morton code.
You could use something like that. I'm not sure. I don't exactly remember, but I know that it can be used because your XYZ axes go from 0 and then based on that, because of that, it forms a code. You know, each vertex actually in the 3D volume forms a particular code of with
Right.
I mean, I'm just throwing up ideas of what you could, what one can. Maybe something which I'd like to. Maybe I'll take a look at your
If you
GitHub and
if you look at if you look up something called the shear warp algorithm, SHEAR WARP, yeah, that's something that treats the space in a very similar way.
right.
Yeah, I don't know a huge amount about that, but I do have some little bit of familiarity with it.
Okay, I'll look it up. I'll look that up, and maybe I'll take a look at your GitHub and see whether I can put in.
Yeah, everything on the GPU is uncompressed,
Right.
so it's all explicitly stored voxels.
Right.
So those are, yeah.